In the last class, I gave a lecture about the STT MNAM, which is a very important application for the modern memory devices with the spintronics. And there is another big branch about the application of the spintronics. That's what we call the race-train memory. Race-train memory. Here, the race-train memory basic working principle is current-induced domain-wide motion. That means the domain can be moved by the current because of the spin transfer torque, or there are other way called the spin orbiter. So first I want to explain what is the meaning of the race-train memory and what's the advantage of them, and then I'm gonna explain about the physics of the current-induced domain motion by the spin transfer torque or other kind of torque. So we already learned about the spin transfer torque, which one is basically by the angular momentum conservation. So in this animation, you can see in the left side, we have a moving electron parallel to the potentiation direction of the one domain. And in other side, in this side, we have a spin, conduction spin in this direction. In other side, we have a conduction spin of this direction. So that means the angular momentum of this spin is changed from this one to the other one. So that angular momentum observed in the domain wall. So as a result, domain wall is moving. That's what we call the current induced domain wall motion. So in this case, the domain wall direction, the moving direction is proportional to the electron flow direction, not the current direction. Actually, the direction of the electron is this way, and the direction of the current is defined by the other way. So sometimes it's confusing, but anyway, the domain wall can be moved by the current. That's the basic principle. Then what happens with this domain wall motion by the current? For example, in this view graph, we have a up domain and domain, and between them we have a domain wall. And this domain wall can be moved by the current. That means domain itself can be moved. So let's back to the hard disk drive. We already learned about the hard disk drive, and as you know, the information is stored in a surface of this platter. That's what we call the platter. And we have a pickup head. So by the rotating this hard disk drive, we can read the stored information in a surface of this platter. Here is the point. We have a read head, and the information is moving. Compared to the DRAM, we have such kind of array, and information is stored each junctions. When we read it, there is no part of the motion of the information. But hard disk drive, mechanical motion part is essential. Because of this moving part, we can store the information in all area, and we need only one pickup coil under the pickup head. So that means if we can make such kind of information storage, we can increase the capacity of the information storage. But the very weak point of hard disk drive is this moving part. Because of this mechanical moving part, make the information storage is unstable. What I'm talking about that is if we have a mechanical shock from the outside, they can make some problem. Sometimes for example, in a surface of this drive, the information is stored something like this, and we have a reading head here, and this distance is just a few nanometer. So if we have some mechanical shock from the outside, there is some chance this moving part can touch the surface of the hard disk drive, then it's gonna give us some damage. So sometimes people compare to this technology. If we have a large airplane called Boeing 747, it's huge one, can fly in a city. We have many buildings. This is outline of cities. Then this Boeing is flight something like this. That's the quite difficult control of the technology. So that kind of a motion in a hard disk drive head is very tricky and very high technology. But anyway, they are very weak for the mechanical shock. And other thing is, we need a lot of energy to rotate the flatter because it's mechanical motion. And also, there is some limitation of the motion, the motion of the hard disk drive, the speed. That means the data access speed is limited by the mechanical motion. So anyway, there are many disadvantages of this concept because of this mechanical motion. Then only one advantage is we can have a large capacity of the information. That's the very important advantage of the hard disk drive. And also, this mechanical motion generates a lot of noise. That's also some problem. Okay. Then what's the meaning of the rest-frame memory? That means if we store the information in such wire, then we can store the information. The blue and red one means the different domain. And we can say this is 11110001001111, something like that. And if we make some reading head and the writing head in one point, and then by sending the current or electron, we can move this stored information, something like this. The reading and writing operation occurred in one side, but the stored information can be moved, something like this hard disk drive. So the information is stored in a domain, not the domain wall, but by pushing the domain wall, we can move the domain. So we can move the information, right? So we can make a very high capacity of the very high capacity memories. So the main advantage of this rest-frame memory concept is somewhat similar to the hard disk drive. We make some mechanical, we can replace the mechanical moving part by the solid state moving part. That's the big advantage. We can reduce the device size, but we can keep the high capacity density of the memory. So in this concept, there are many research occurred. This is a basic principle. If we have a nanowire here and stored information, then we have a read-write head. Then after by the spin transfer torque, we can moving the stored information here. Okay, and that means we can make a capacity and cost is comparable to the hard disk drive, but we have a much reliable and very high performance of the solid state memory. So that attractive to the it is very attractive idea. So many industry started to involve this research. And the working principle of this domain motion is based on the current-induced domain wall motion. Okay, then we should think about the domain wall motion. First, I'm going to explain by domain motion by the field. Okay, so in a domain motion, Chang asked me in a Western movie, there is some kind of we are using the current, so he is worried about the Joule rating, right? So that's the very important. So if we can move the domain wall with the current, with the very low current, then Joule heating is not a problem. But if we have if we are using a very large current, then the Joule heating is very important. So actually, the most of the research about this domain motion by the current is focused on how we can make the current, the domain motion with the small current. That's one of the key research. But so far, the energy, how can I say, the moving of the energy required to domain motion is it's not that large. You can make it very small, ideally, but practically it requires a huge current. So we have many things to in many topics to reduce the current density in this topic. Okay? So that's a big, very important point. Okay. So domain motion by the current, this is the x-axis, the field, and the y-axis is domain velocity. So in a small field, the domain motion moved proportional to the external field. The velocity is proportional to the external field. So we make some kind of linear velocity increasement with the field. And this region we call the steady domain motion. We're going to learn about this. And then there is some certain decrease of the voltage and the velocity. This point, what we call the Walker breakdown. And then domain velocities decrease, even we increase the field. And finally, they are start to proportional to the external field again, but different slope. So in this region, we call the precession region. So domain motion by the field, we have generally this kind of velocity dependence with the field. And also the domain motion, we divide by two regions called the steady motion, and the other one is precession motion. But this idea is, without any imperfection of the without considering the thinning of the domain wall. So in a reality, the domain motion velocity with the field is something like this. With the small field, the domain wall cannot move, or they are moving with very, very slow velocity. That's what we call the creep motion. And if we applied some large current, then compared to the some critical current called the deepening field, then domain wall moving something like this. With increasing the field, the velocity is here. But in a zero temperature, domain wall cannot move when the applied field is smaller than the deepening field. But in a finite temperature, we have some domain wall motion, very slow. But this motion is important in many research. So this region we call the creep motion of domain wall. And this can happen in this cartoon. If we apply the field larger than or comparable to the thinning field, the domain wall can moving such kind of overcome such kind of energy barrier very easily. But if the domain wall, the field is smaller than the deepening field, then there are many energy barrier in a motion of domain wall. So the domain is stabilized in this local energy minimum, but there are another minimum here, but we have to overcome this energy barrier. So to overcome this energy barrier, we need the final temperature. So it's kind of a tunneling. not the physical, the real tunneling, but in a sense of the energy, we have some chance to move to domain from one place to the other one. So this is what we call the creep motion. So in a small field means the smaller than the pinning field or critical field. There are many names, but in this region, the creep motion is very important in dominant. And in this case, the thermal activation means the thermal, without the thermal energy, we cannot move the domain wall. So higher temperature means we have a large domain wall motion. The thermal activation motion is with the energy barrier is the basic idea of the motion of the domain wall in a creep region. And this is the related to the pinning and the depinning process of the domain wall. And also the domain wall motion in this case is not very continuous. They are kind of discrete jump from the one pinning point to the other one, something like this. Okay. Then, oh, by the way, I should explain about the pinning, domain wall pinning. Okay. As you see here, the domain wall energy has such kind of energy barrier depends on the pinning site. Pinning site means some place that can hold the domain wall. For example, the domain wall energy is something like this. Oh, sorry. This is the domain wall width. Domain wall energy is like this. So that means if we have a domain wall here, this boundary, for example, we have a up domain and down domain with a domain wall here. Then this wall has this surface energy. Then just think about that. If we have a domain wall, something like that, but oops, they're moving one direction to this one. But if we have some kind of a point where the exchange is constant or energy is different. So in this point, domain wall energy can be changed. So when domain wall touched this pinning side, this part feel the different energy. They can be larger or smaller than the domain wall. Then that means we have, for example, this is larger than the other area. Means if we have a large anisotropy in this focal point, then domain wall feels some kind of a barrier, energy barrier here, because in this one-dimensional plan, we have a large energy domain wall region here. Means if domain wall is moving to this direction, there's no energy difference, so they can move very easily. But when they meet this energy barrier, if domain wall touched this area, that means we can increase the system energy because of the large domain wall. So they start to bend domain wall, something like this. That's what we call pinning. Then the domain wall length is increased compared to here. So that means the total energy is increased because the domain wall energy is meaning of the surface energy per area. So if we multiply the area, we can obtain the energy. So that means if you increase the domain wall length, energy, the area is increased, so the total energy is increased. So when this increasement of the energy is getting larger than this part, then domain walls past this domain, the energy barrier, and then flat again to reduce the domain wall energy. So this kind of imperfection act as a domain wall pinning side. In the other way, if we have a smaller domain wall energy in this area, we have some kind of potential well. So domain will easily go inside of this imperfect, in this pinning side. But after that, they feel very comfortable in this low energy state. So they don't escape again, because we don't, to escape this pinning side, we need certain amount of domain, the extra energy. So they also make such kind of pinning. Okay. So this is the main idea of the pinning of the domain wall, some kind of pinning site. So this can be happens in any perfect samples. I'm sorry, if your sample is really perfect, there is no pinning site. But in reality, always we have such kind of defect because of the many reasons. So somehow we have such kind of a pinning site. Then the domain motion is mainly governed by the pinning depinning process. And as a result, we have a dominant cream motion. But if we have a large enough external field, such kind of energy barrier is much smaller than the pinning external field, then dominant motion is moved very easily. So, as you see here, we have a lot of pinning site here, pinning site. So domain wall is pinned in this pinning site, and this pinning site generally randomly distributed in your sample. So in order to overcome this pinning process, you need to make really good samples, or if you applied very high external field, then pinning field is not so important. But anyway, let's keep talking about this cream motion. This kind of energy barrier is can be described by the energy barrier height, or this is two kind of energy barrier, potential well or potential barrier. Anyway, we can say so the height of the or depth of the potential well or barrier is U, you see. And kind of energy barrier can be overcome by the thermal energy. So we have such kind of domain motion velocity with the external field H external. That's the came from the Arrhenius law. Here the beta is 1 over kBt. So this here beta is here. So UC over kBt means the competition between the energy barrier and the thermal energy. Okay. So this exponential term, this part is a ratio between the thermal energy and the energy barrier. And the other part here, external field is normalized by called the critical field. So if we have a large part here and small part, I'm sorry, if we have let's think about the fixed this term, because the UC, the energy barrier, is determined by your sample, and beta is determined by the temperature. So this is generally fixed one for a given sample at given temperature. Then we can adjust the external magnetic field. And if we apply large magnetic field compared to the critical field, this term can be, the exponential term can be going to 0, going to 1. But if we have a small field, and this number give a much smaller value to compared to 1. So this V0 is some kind of maximum velocity of the field-driven motion. But with the small field compared or comparable field to the critical field, the domain motion velocity is getting smaller compared to V0. So if we taking some experimental data of the domain motion velocity, with a given external magnetic field. And then if we plot it with the logarithm in the left-hand side, we can obtain this form. Here is one example of the experimental data. In this case, the intersection gives us the log V0, and the external field, if we plot this experimental data with this unit here, this plot is given by 1 over h power 1.4. So that number, 1 quarter, is came from some statistical physics with the dimension of the problem. For example, this mu, the exponent mu, is given by this relation here, and this zeta number is came from the dimension of your problem. So for the thin film and the domain wall, we have a mu value of the 1 over 4 quarter. So this is quarter, and that's why we have it here. And as you see here, the motion of domain velocity is quite linear to this value. And as you see here, the log V is covered from minus, let's say, 20 something to almost to positive value. So it's quite large variation of the velocity V because it's logarithm scale. So in this large range of the domain velocity, they can understand, they can be explained by this kind of simple motion. Okay, so this domain cream motion is very important to understand the basic domain motion, and also many experiments we can obtain such kind of velocity in a cream motion. Okay, so actually this cream motion is not that familiar to the student, but just remember that many things can be happens by this cream motion in a small field. Okay, so let's think about that with the field of the domain motion. In this cartoon, I represent the magnetic direction with the blue arrow and the red arrow in two domains, and there's a domain over here. And with the external magnetic field, because of the Gman energy, that means the magnetization prefers the parallel direction of the field. So to lower the energy system energy, this domain part is enlarged, and this part will be shrink down. See this cartoon. If we have two domains in a right hand, the right direction, and other domain in the left direction, with the external field, this domain area is getting larger, and this domain area is also getting larger, but this domain area is getting smaller. Yeah, this is the result of the energy minimization, especially the Gman energy. So this energy equation, you can easily understand the domain of the parallel direction getting larger and the domain of the opposite direction getting smaller. But it doesn't tell us about the details of the domain dynamics. They are talking about only the domain enlarge or shrink down of the domain. So in order to understand the domainal motion with the field, we need something more. Okay. Let's think about this domain structure again. Here is one domain, here is another domain, and there is the domain one. With the external magnetic field, let's think about the energy equation. In this magnetic moment, we have a parallel field. So there is actually no torque, zero, because they are parallel. And also, this part, we have opposite direction of the field, but still, the torque is still zero because they are anti-parallel. The torque of the because of this external magnetic field is acting only this non-collinear part. For example, this one, we have an external magnetic field here, we have a magnetic moment here, then there is some precession torque. And there is some damping torque in this field direction. You see, here this is the damping part. So this precession part make the domain wall precess, not aligned to the field direction as we already learned. Please remember this graph. With the external magnetic field, the magnetization starts to precess, and this precession doesn't change the energy of the system. Only this damping part can change the energy to the lower part. So this damping part, in other words, called the damping torque, this damping torque moves the magnetization direction to the field direction. So this precision part plays some roles, but in this case, the damping part is more important. Okay. So please keep in mind that damping is very important in this domain motion. So from now on, I'm gonna explain the details of the domain dynamics with many mathematics. Actually, if you take a look this paper, there are I took many things from this paper. Actually, from these cartoons and also these equations. So please read this paper if you wanna study more. Okay, first let's think about the domain wall structure in for example, the PMA material here. If we have up domain here and the down domain in other word, in other side, then we have a domain wall, this structure. And let's define the domain wall with the delta. And in the in-plane case, we have also similar things with the domain wall is delta. And inside of the domain wall, we can define the direction of the domain wall by this equation. This equation means actually tangent theta. Here the theta is angle from the z-axis. It's given by this form. Here y0 is the domain wall center. So that means if we have a domain wall center here, then this gives number 1. So theta over 2 should give plus minus pi over 2. So we can drop the 2, then theta should be plus minus pi at the domain wall center. Oops, something wrong. Just a moment. Oh, sorry. This is pi above. So theta should be plus minus pi over 2. So that means at the domain wall center, the theta value is plus minus pi over 2 means they should be in plane. Okay. And in other words, if we have a plus infinite of the domain wall place compared to the domain wall center, then this number give a large, then exponential term give us infinite. So in this case, the theta if we tangent theta is infinite means the theta should be plus minus pi. So that means up or down direction of the domain monetization. And also, if we have a minus infinite case, minus infinite, then this term give a 0. So in this case, theta is 0. So that means the up domain. Okay. So this equation gives us the details of the domain world monetization direction inside the domain world. And actually, you can obtain this result by the variational principle in a domain world structure. Okay. So anyway, let's offset the domain world structure in this form. And here the delta domain world width is given by this equation. Here, if we taking out this part, this is nothing else but we learn from the initial anisotropy energy. And this Nx, Ny, Ng is came from the shape anisotropy of your samples. So in a thin films, and if we think about the ideal block wall or needle wall, we have a little bit different shape. So anyway, this additional term is came from the shape anisotropy, and this is the intrinsic anisotropy. So this is actually total anisotropy of your system. And here the block wall is called the when phi is 0, and if phi is the pi over 2, then this is the ideal, the nil wall. So the phi is the angle, azimuthal angle in our xy plane here. So if blow wall means domain wall is confined in yz plane, something like this here. So domain wall is moving yz plane from this up direction to the down direction here. Then they are moving something like this. Like this. That's the blow line, blow wall. In a needle wall, we are talking about the phi is 2 pi means. Sorry. In this case is GY plane. Okay, so I just talk about the real type domain wall here in the YG plane, and in a blow wall, the domain wall is confined in a XG plane. Here. So in this case, the domain wall propagation to the Y direction. So let's start from the plus up domain, and then let's say this up domain here, and down domain is in different Y. So domain wall is formed by the rotating the magnetic moment inside of the Y plane, like this. So please remember that the domain wall of the block type and needle type has a different rotation of the magnetic moment inside of the domain wall. Okay. So can you understand what I'm saying about the difference of the block and the needle wall? Okay. Okay. Yeah. Then anyway, so please keep in mind the domain wall width is ratio of the exchange energy, which one prefer the domain wall is the magnetic direction is parallel. And the anisotropic energy means they prefer the specific directions. So they want to keep the domain wall width is getting smaller. And this exchange energy try to narrow down the domain wall width. So that because of this competition, you can determine the domain wall width and the domain wall energy. Okay, so from now on, I'm using some mathematics, the spherical coordinate system. So you should remember that this relation. You can convert x, y, z unit vector to the r, theta, phi of the unit vector. Or you can convert from r, theta, phi to the x, y, z unit vector. This relation you can find any mathematical physics book. And nowadays you can easily find it, such kind of relation in a internet very simply by the Wikipedia or many mathematics related site. So please remember that this relation, I'm going to use it many times. And this spherical coordinate system, we can determine the unit vector to the r direction and the theta direction and the phi direction. Okay. So in this relation, if we have any kind of field, we can determine the torque. And this torque vector is represented by the r component and theta component and the phi component. Okay. And this is theta dot means the time derivative of the theta. And this is nothing else but the this is the torque theta component here. And if you multiply the minus gamma over ms, then you can convert the torque to the angular motion. If you think about that, the magnetic moment, and the angular momentum has a relation with okay. So the ratio of the ms, the angular momentum over ms is gamma, right? Oh, it's the way. Sorry, the ratio of the magnetic moment over the angular momentum is given by gamma. Okay, so the relation between the torque and the time derivative of the angular momentum give us torque. So we can make some relation between the theta dot to the torque of the system with the proportional constant of minus gamma over m. It's the same for the phi direction. So if you obtain the torque to the theta and phi direction, we can obtain theta dot and or phi dot. But we are not considering this part because this r is the magnitude of this magnetic moment, which one we consider the constant. The magnetization direction can be changed, but the magnitude is always ms. So it's kind of unit sphere. We are talking about the unit sphere. So the derivative time variation of the magnitude is always 0. I'm sorry. This dot is always 0. So we don't need the equation for this equation. It's always 0. Okay. So our purpose is finding this relation because we want to solve the dynamics of the spin. means if we solve this differential equation, or if we obtain the theta as a function of time and phi with the function of time, then the solution is what we want. Okay, so what we have to do is finding this torque term. So let's start the easiest one. The precession torque due to the external field, H0. And let's make the H0 is parallel to the g-axis. Okay. Here. And the mass moment M is actually nothing else but the magnitude of the ms and the direction of the r vector. The r vector is defined by the magnetic direction, so this is simple. So we have this relation. Okay. And what we have to do is we have to solve, we have to rewrite this expression. This expression is generally not that easy because we want to write down this is in a spherical coordinate system. So we have to change the g vector to the spherical coordinate system here. The g vector is from this relation. The unit vector is this form. If we multiplied this one. Okay, and if we multiplied r here, this part is going to 0, and this part is also going to 0 because r parallel. We have only r cross theta term here. And r cross theta give us 5. So it turns out this form. The r cross g is here. So we can see this result. That means in a r theta phi representation or polar coordinate system, the torque of the this precession term give us only phi component here. So this is what we already learned. So in a precession motion, if we have magnetic moment here, precession motion means they are rotating in this circle. So they give only variation of the magnetic moment in this direction. This is nothing else but the phi unit vector direction, right? So actually, this is the what we already know. If we have M cross H, we have a MSH0 sine theta because of the angle between the MS and H0 is theta. And then the direction is perpendicular to these two directions, both directions. So now we have the field direction here, magnetic moment here, and they made some plans, and this vector must be perpendicular to this plane. That's nothing else but the phi. Okay. Yeah, if you have any question during this my derivation, please ask the questions because there are many mathematical expressions, so it may be confusing. Okay. Okay, and there is one important comment. In a domain wall, inside of the domain wall, there is some torque because of the energy and the unelastic energy. But they always compensate each other by forming the domain wall. So that means in this calculation, we assume the domain wall shape is not changed. They are always keep this form. And this domain formation came from the balance between the exchange torque and the anisotropy torque. So we don't need to care about that. Okay, so now we are focusing on only the external magnetic field. And we have a torque because of the field is something like this. Yeah. And let's think about the damping torque. This is the damping term, and let's define the damping torque in this form. Here, let's do it again. In alpha over gamma is here, and we have a magnetic moment, which one is MSR, and this is also MSR. So we have a 2 MS, and 1 MS is dropped with the cancelled by this term. So we have a 1 MS here, remaining 1 MS here. In other one is the only the unit vectors. Okay, so this N has a unit vector R here, and we have a cross product, and this part is for DMDT. Okay, so how we can obtain this part? That's a little bit tricky, but you can find it also in mathematical physics. Here, if we have a R vector time derivative, then this is a DDT, the total derivative. So we have such relation. Means in this derivative, this R vector is R, the magnitude of R and the R unit vector. So when you take in the derivative, we have to take a derivative to this part. Sorry. In this case, we need such relation. Okay? So this is what I'm saying. These two parts. And fortunately, this part is going to 0 in our case because the R dot, we assume the magnitude of the R is always 0, always constant, so it's going to 0. But let's keep in the general case. So we have this term first. And what is this part? This part, we have such relation. In a derivative for the R unit vector, generate these two terms, and time derivative to the theta unit vector, we have this one and this one. So we can put this one here. Okay. And how can you prove this one? So, for example, here, this equation, R unit vector is the difficult thing is here. The x, y, and g unit vector is time independent, but the r, theta, and phi is changing by the time. They are function of the time. Because the magnetic moment direction, the theta phi is changed. So if we take in the time derivative here, okay, then this part is cosine theta dot sine phi x plus sine theta minus sine phi dot x. And the second term here is cosine theta dot sine phi y plus sine theta cosine phi y dot. And minus sine theta dot g. Yeah, it looks very complicated, but if we're taking out the zeta dot together, we have a all this term has a zeta dot. And if we're taking out the zeta dot, then this is nothing else but this one. So this part is zeta dot and phi hat. And this part, if you're taking out the phi dot, then we have this one. This term give us, if you're collecting phi dot and sine theta, then the remaining part is phi hat. Okay, so we have these two terms for the time derivative of t, the r hat. So this is the result. Okay, and you can do it same thing for the theta and phi, and you can obtain such relation with this equation, this relation. So it's very, it's not easy, and you need many tedious calculations, but somehow you can do it. So anyway, so you can insert this result here. Now we obtained this term, or we need this term actually, and we have this relation. So we can back here. That's why we have this one. Okay, now we are totally working on in polar coordinate system. So the remaining problem is we have r hat cross theta hat, r hat cross phi hat, and this give a phi hat, this one give a minus theta hat. So this is the r component, theta, and phi component. So this term give a phi component with the theta hat, sorry, theta dot, and this term give us minus theta hat, so we have a minus phi dot sine theta here. Okay. So finally, we can obtain the torque because of this damping term in this polar coordinate system. Is it okay? Okay. Then there is the damping torque, sorry, the dynamic field torque. That's the little bit difficult one. If we define the damping and the dynamic field, which one is generated by the Shell entropy, we have a torque because of this H dynamic field. That's the little bit difficult part, but very important in the dominant motion. So let's think about the H dynamic field is defined by this relation. We already learned that. The H dynamic field is this relation, and the N is the dynamic coefficient, dynamic tensor. And fortunately, if we play with the principal axis of the ellipsoid, we have a diagonalized element. But generally, they have a off-diagonal element with non-zero value. But anyway, so this tensor is defined by the XYZ coordinate system. So let's do it here. The mu zero ms square came from the one ms came from the dynamic field, and the other ms came from here. So they are proportional ms square. So this is the unit of the energy per per volume. Okay. Here, this m vector generate the r vector here, and this term give us the nx, mx, and ny, my, ng, mg. Means this external field, the Dirac field, is x component, y component, and g component of this form. Okay. And this matrix is nothing else but this one. Okay. So in order to convert the XYZ coordinate system to the polar coordinate system, we need this matrix. And the mx, my, mg is nothing else but x component, y component, and g component in a polar coordinate system. So x component should be sine theta, cosine phi, and y component, g component. Okay. Then let's do matrix operation. If you multiply this vector to this polar coordinate matrix, then transform matrix, then you can obtain this form. Oops, something wrong. Sorry, it should be just a moment. Sorry. In this multiplication, we have a r, theta, and phi component. Yeah, if we multiply this to this one, we have something here, and this one multiplied by this one, we obtain this one. And here I just skip this part because we have a cross product with sorry. I'm sorry, I made a mistake again. The previous one is correct. Sorry, just a moment. Okay. If we multiplied this one, we have this part, and this one give us this part, and this one give us 0. Because if we multiply this term to here, sorry, sorry again, this is not 0, but we have something here. Anyway, so let's do the cross product of R vector. This is the R vector vector, theta vector, and phi vector. Then, because of the cross product of R, will be going to 0, and R theta give us phi, and R cross phi give us minus theta something. So eventually we obtained final form of this one. Because this cross product of R, we have a 0 component in R component, and finally we have a theta component and phi component of the damping torque. I'm sorry confusing this part. I will check it again and then correct it. So anyway, now what we obtained so far is here. This is the appreciation torque and damping torque and the Dmax torque, right? And this torque is also, we can say, this torque component is also R torque, theta torque, phi torque. And please remember that this torque component is related to theta dot and phi dot. So we can write all this equation together, but there's no R torque terms. We have two torque equations as torque here, theta torque and phi torque. And if we multiply this term, we can obtain the theta dot and phi dot. And this equation, theta term is this one. Therefore, this term. Okay. And phi torque, we have this term here, this term here, this term here. This is the result of the torque in a domain world. Okay, the remaining problem is now we can solve this differential equation. But here we have a theta dot and phi dot here, and phi dot and theta dot here. So they are actually coupled to differential equation. Actually, we did it a very similar thing, when we solving the error equation. Actually, this is error equation, but at that time we play with the x and y component. But now we are talking about the theta and phi term. What's the difference? In this error equation, when we are solving, we assume the first order perturbation theory. We assumed this mx, my are smaller than the ms, right? So we assume the signs, the harmonic motion of the magnetic moment with the external disturbance. But here we drop such kind of assumption. This is the more general expression, more general term. Okay. So you can apply this technique to the error equation also. Okay. Okay, I think today's lecture should be started here. For today's lecture, by the way, for the final exam, yeah, I'm gonna show the final result first. In a field-driven motion, domain velocity can be just a moment. Yeah, that's the one of the final result you can obtain. Here, we have a two part. One is steady part and this precision part. This is a result of the precision part. And this domain or velocity is determined by something here. Here, this alpha divided by 1 plus alpha square is approximately just alpha. So this is about 0.001. And this gamma is 0. I already said many, many times, if we multiply the gamma to the field, we can obtain the frequency. And you may know this is the frequency of order of gigahertz. Sometimes it's 10 gigahertz with the strong field. And this is the unit of the inverse of time. In order to obtain the domain velocity, should be meter per sec. And this alpha is dimensionless. So we have a frequency term here, and we need some length scale. And in a length scale, in a domain motion, the domain with the most relevant length scale. So that's the expression of the domain velocity. So in this framework, if you apply the larger field, then you can increase the frequency as you want. But in a typical way, this is the, let's say, the domain is around, for the simplicity, is on order of 10 nanometer. And this frequency gives us about 10 gigahertz, something like that. Then the gigahertz can be dropped with the nanometer, we can obtain the meter per sec. So that means 10, 10, and we have a 0.01, so it gives order of meter per sec in this condition. But if you obtain the something more here, then you can obtain even larger velocity. But in a precession motion, we have this relation, but let's think of the steady motion. The steady motion, we have a very similar relation, but a little bit different form of the alpha. Alpha is in a denominator. This part is actually same. So they generate order of 100 meter per sec with divided by alpha. So in a previous case, alpha is multiplied by here. But in this case, we have a alpha is in a denominator. So they can be much larger than this one. But the problem is, in order to obtain such velocity, we applied moderate field, but they are larger than the Walker breakdown field. So we can go this way with the field, but in certain field, this solution is no longer valid. So we should go to this solution. So we have it here. Okay. So that's why we want to make the large Walker breakdown field. Maybe that's too much today. I'm going to explain more details in next lecture. It's time's up. So let me say about the final exam. I'm going to give some final exam problems, but you guys can bring any kind of textbook or lecture note. So it's kind of an open book. So if you want, you can search internet. So bring your cellular phone, but don't communicate to each other. That's the rule. Okay. So you don't need to remember many equations, but you should understand how you can drive and what's the physical meaning of them. Okay, so if there is no more question, let's close today's lecture.